Neptune just defied the pattern planetary auroras were thought to follow. For the first time ever, astronomers caught it glowing, and the lights weren't anywhere close to where they should be. On Earth, Jupiter, and Saturn, the magnetic poles lie close to the geographic ones. As a result, auroras glow near the top and bottom of each world, exactly where we expect them to appear. On Neptune, the lights appeared somewhere else entirely. Imagine Earth's northern lights abandoning the Arctic and flaring above Mexico. And the reason why reveals something deeply strange about the forces surrounding the farthest major planet in the solar system. A world that has been hiding its secrets for 34 years in the darkest corner of our planetary neighborhood. In 1989, NASA's Voyager 2 became the first spacecraft to encounter Neptune at close range. It sent back images that changed everything scientists thought they knew about the planet. A brilliant blue world, far more dynamic and active than anyone had predicted. And buried in its data were faint hints of something unusual in the upper atmosphere. They suggested that Neptune might produce auroras, the same glowing lights that appear above Earth's poles, but the hints were too faint to confirm. For more than 3 decades after Voyager 2, telescope after telescope searched for those lights. Every attempt came back empty. Neptune remained the only giant planet in the solar system where auroras were expected, but had never been directly observed. Then the James Webb Space Telescope pointed its instruments at Neptune. And the lights were there, but finding them was only the beginning. The real mystery was where they appeared, and solving it meant first understanding the world beneath the glow. Neptune is not a planet that invites close study. It orbits roughly 2.8 billion miles from the Sun, about 30 times farther out than Earth. Sunlight reaches Earth in about 8 minutes. It takes nearly 4 hours to reach Neptune. By the time those rays arrive, they're roughly 900 times fainter than the sunlight Earth receives. At noon on Neptune, the sun would appear not as a blazing disk, but as an unusually bright star hanging in a twilight-like sky. Average temperatures on Neptune hover around minus 330 degrees Fahrenheit. Its atmosphere is mostly hydrogen and helium, with methane helping to give Neptune its blue color. From the outside, the planet appears calm, cold, almost motionless. That appearance is completely wrong. Neptune has winds measured at speeds exceeding 1,200 miles per hour, among the fastest ever recorded on any planet in the solar system. To put that in perspective, the most powerful hurricanes on Earth reach wind speeds of around 200 miles per hour. At their fastest, Neptune's winds move 6 times faster than that, racing across the face of a planet with no solid surface beneath them. Storms form and sweep through its atmosphere. Enormous dark spots churn through the upper atmosphere, the same type of storm Voyager 2 discovered in 1989. Measurements indicate that Neptune radiates about 2.6 times as much energy as it absorbs from the sun. That extra energy does not come from sunlight. Much of it is thought to be left over from the planet's formation billions of years ago and is still radiating outward today. The same process that keeps Jupiter and Saturn glowing brighter than sunlight alone could explain. But Neptune's internal heat was not what produced the glow Webb detected. To follow that trail, we have to turn back to the sun. Auroras on Earth form through a process that, once understood, seems almost elegant. Charged particles stream outward from the sun, forming the solar wind, which spreads through space in all directions. When it reaches Earth, most of it is deflected by our planet's magnetic field, but some of its energy is transferred into Earth's magnetic environment, accelerating particles along the field lines towards the poles. There, collisions with gases high in the atmosphere produce light, shimmering curtains of green and red, known as the northern and southern lights, glowing above the Arctic and Antarctic. Neptune was expected to follow the same pattern. It did not. When Webb captured Neptune's auroras using its near-infrared spectrograph, the glowing regions did not appear at the poles. Instead, Neptune's auroras glowed across the planet's middle latitudes, roughly the same range as Earth's subtropical regions. The geography of the glow was wrong, and it was wrong in a way that immediately pointed towards something unusual about Neptune itself. The reason lies in Neptune's magnetic field. On Earth, the magnetic field is generated by the movement of molten iron in the planet's liquid outer core. It's tilted by only about 11 degrees from Earth's rotation axis, so the magnetic poles lie close to the geographic poles. That's why the lights show up where you expect them. Neptune's magnetic field is tilted by about 47 degrees from the planet's rotation axis, more than 4 times Earth's tilt. That alone would make Neptune unusual, but there's another twist. Neptune's magnetic field is significantly offset from the planet's center, causing its strength to vary dramatically across the planet. One region can experience a much stronger magnetic field than another. Imagine Neptune's magnetic field as a giant bar magnet inside the planet. It is tilted by about 47 degrees and shifted far away from the planet's center. As Neptune spins, the field turns with it, constantly changing how it meets the incoming solar wind. Instead of funneling charged particles toward the geographic poles, Neptune's unusual magnetic field guides them toward different regions of the atmosphere. That's why Webb found the auroras near the planet's geographic mid-latitudes instead of near its geographic poles. But the location was only the first surprise. Finding the glow wasn't enough. Scientists still needed definitive proof that what they were seeing was truly an aurora and not some other atmospheric phenomenon. That proof came from a molecule called H3+, the trihydrogen cation. You don't need to remember the name. What matters is what it tells us. When charged particles slam into hydrogen high above Neptune, they leave behind H3+ like fresh footprints in snow. Detect an unusually high concentration of those footprints, and you're no longer looking at a mystery. You're looking at an aurora. Scientists had searched for this signal on Neptune for years, using the best ground-based observatories available. Every search failed. From the ground, Neptune's extremely faint H3+ emission was difficult to separate from the sunlight reflected by its bright clouds. And as Webb later revealed, the signal itself was far weaker than scientists had expected. But Webb's highly sensitive instruments, operating above Earth's atmosphere in the cold of space, detected an unmistakable H3+ emission in Neptune's upper atmosphere. Nearly 3.5 decades after Voyager first hinted that the lights might exist, Webb finally provided definitive proof. Neptune's auroras were real. The mystery, it seemed, was over. But the confirmation immediately opened a new question. If the auroras had always been there, why had they stayed hidden for so long? Part of the answer is simply distance. At 2.8 billion miles, Neptune is so far from the Sun that the solar wind's influence has weakened considerably. With fewer energetic particles reaching the planet, its auroras were likely to be much fainter than those on Jupiter or Saturn. Distance explained part of the mystery, not all of it. Webb uncovered something else. By measuring Neptune's upper atmosphere in infrared detail for the first time since Voyager 2's flyby in 1989, scientists found something nobody expected. The upper atmosphere had cooled by several hundred degrees. In fact, by 2023, it was just over half as hot as Voyager had measured more than 3 decades earlier. That dramatic cooling made the H3+ signal far dimmer, pushing it below what ground-based telescopes could reliably detect through Earth's atmosphere. The auroras had likely been there all along. They had simply become too faint to see. Scientists still don't know what caused Neptune's upper atmosphere to cool so dramatically. The challenge is that the comparison relies mainly on just 2 measurements taken 34 years apart. Voyager 2 in 1989 and Webb in 2023. With so little data, the reason for the cooling remains a mystery. Every answer Neptune provides seems to uncover another question. That pattern is becoming difficult to ignore. To understand what the aurora discovery might mean at a deeper level, you have to go beneath the clouds. Imagine diving beneath Neptune's blue clouds. The deeper you go, the more the pressure builds. Water, ammonia, and methane are squeezed into an incredibly hot, dense fluid. Not quite a normal liquid, not quite a gas. Deep inside Neptune, scientists believe there may be a small, dense, rocky core, roughly the mass of Earth. At those depths, pressures reach millions of times Earth's atmospheric pressure. It's an environment so extreme that matter no longer behaves the way it does on Earth. The laws of physics never break. They simply play out in unfamiliar ways. The magnetic field that determines where Neptune's auroras appear is generated far beneath the atmosphere. The exact mechanism is still not fully understood, but scientists think Neptune's magnetic dynamo may operate within a relatively thin shell of electrically conducting fluid deep inside the planet, rather than in a liquid iron outer core like Earth's. Models show that a thin shell like that could produce a field that's tilted, offset, and far more complex than Earth's. And that would explain why the auroras Webb detected didn't line up with Neptune's geographic poles. But the planet's story becomes even stranger with Triton, its largest moon, which orbits in the wrong direction. Among the largest moons in the solar system, there's a clear pattern. They orbit in the same direction as their parent planets rotate. Triton breaks that pattern. Its retrograde orbit strongly suggests that it did not form alongside Neptune. Scientists think it was originally a Kuiper Belt object before being captured by Neptune's gravity billions of years ago. Voyager 2 found active nitrogen geysers erupting from Triton's frozen surface, a world so cold it sits at around minus 391 degrees Fahrenheit, yet it still vents material into space. Triton's orbit is also slowly shrinking. Over billions of years, tidal models suggest it could move close enough to Neptune to be torn apart, potentially forming a new ring around the planet. Like Neptune itself, Triton is a reminder that Neptune's system still holds surprises. Webb's aurora discovery closes a 34-year chapter in planetary science, but its significance extends beyond Neptune itself. Neptune is an ice giant, and planets roughly its size appear to be surprisingly common throughout the galaxy. Understanding how its unusual magnetic field produces auroras far from its geographic poles gives scientists a nearby benchmark for interpreting distant worlds. We have visited Neptune exactly once. There is currently no approved mission to return with a dedicated spacecraft. For now, every new answer must come from watching a tiny blue world billions of miles away, which makes you wonder how much is still out there, sitting in plain sight, waiting for us to look again.